everyone. Welcome to our Tuesday afternoon session to the land of yet another Nobel laureate. So today we'll have two talks this afternoon. One by Iason, who will tell us about dark matter during supercooled confinement. And then one by Yuri Smirnov that we'll hear later. So for the time being, let's hear from Iason now. Thank you.
Okay, so thanks very much, and thanks to Filippo for inviting me to talk about his work, and also to the other organizers for not objecting too much. So this is, I'll be presenting this work I did with Jan, Filippo, and also Geraldine, and this second paper will be with Geraldine. So first, let's have just a brief review, because this is going to be about composite dark matter, and obviously there are many options for such dark matter. And we saw a tour of possibilities in the talk by Michele yesterday. And okay, I don't list all the references. Lots of people have worked on this topic. And what one quickly realizes, of course, is that to estimate the relic abundance in these sort of dark matter models, it may be important to consider both the deconfined and confined phases, so that you have a picture of the evolution of the universe throughout its history. And I think our talks are going to be on similar topic. And so just to put everything, make everything clear from the start. So, what's the difference? What are the different assumptions being made? So Yuri later on will be talking about composite dark matter with heavy quarks, in which the phase transition also plays a role. But what's very important there is that the quarks are heavier than the confinement scale. So we'll be hearing about that in a little while. So the picture I'll talk about here is composite dark matter made of light quarks. So quarks which are lighter or approximately massless compared to the temperature, and also the confinement scale when the temperature of nucleation. And I'll be talking about what happens in a strongly supercooled phase transition with ultra relativistic walls. So of course you might go in some parameter space, some theory, some model where you don't have a strong phase transition at all, then this doesn't apply. But in this limit is what we're going to be looking at exclusively, almost. So this will first I'll talk about diluting dark matter during a phase transition, just some very generic comments to put everybody on the same page, and then talk about the composite dark matter from supercooling, which is what we worked on, and extend that also into a picture of a dilaton portal, where the dilaton communicates both to the standard model and to the strong sector, the exotic strong sector. And then I'll also, at the end, briefly discuss the gravitational wave signal from supercooling. So this slide, everybody's going to be very familiar with this. So you have we know the cold dark matter, the energy density today, and then of course we can translate this into a number density. And for heavy dark matter, so okay, here I put the reference scale TeV, you're going to have to suppress the UV thermal value. Okay, of course we all know this. So if it's come into equilibrium early in the universe, we need to suppress this thermal value. And the standard way to do this is to have a large annihilation cross section, so that the dark matter stays in equilibrium long enough, and it stays in equilibrium until it's non-relativistic. The number density becomes Boltzmann suppressed, and so on. And then this is limited by unitarity to dark matter masses below about 100 TeV. And then there were some papers talking about different aspects of this. I wanted to also highlight Yuri's very nice paper on this. So there we are. Of course, we know also that there are many ways to get around this limit. One simple way is through dilution of the dark matter. What's been studied a lot, of course, is that you have a matter-dominated epoch. So you have some additional expansion, some field which lives a long time. For example, like in the pions we heard about yesterday, and these lead to an entropy injection and then a dilution of the dark matter density. An alternative to having a matter-dominated epoch would be, of course, to have an inflationary epoch. So I'm not talking about the usual slow roll inflation, which takes place much earlier, but some other time in the evolution of the universe that you have some exotic scalar field, say, which gets stuck behind the barrier in its effective potential. So we know the temperature corrections to the potentials of scalar fields are very important. So you can start off in the global symmetric phase here, where you're at the start in a global minimum, and then have the potential evolve with temperature so that you get stuck behind a barrier. And then this field will tunnel through here and go to this broken phase, go to the true vacuum state. But this tunneling or excitation over the barrier can be delayed. So if this happens, you're here at this state with a large cosmological constant compared to like the small CC we observe later on in the universe. And so inflation will start when this energy density from the large CC becomes becomes of the same order same magnitude as the radiation energy density. And here in the picture we're interested in here, the temperature of nucleation will be far below the scale of this VEV here. Yeah? And then when this happens, so we enter this inflationary epoch, and when the phase transition finally takes place, there's not a lot of plasma around typically, and the bubbles will accelerate until they collide. And you have this picture where the vacuum energy density that was present there just before the phase transition goes into the bubble walls, and these eventually collide. You have some oscillations. So when the fields from opposing bubbles collide, it'll be a violent process, and you'll have some oscillations about this minimum. You can just imagine some crazy fluctuating scalar field, and you'll have these oscillations, and then you'll have eventually you'll have this field oscillating here, and then it'll decay in a model-dependent fashion back into radiation, reheating the universe. And chemically decoupled species from before the phase transition, if they don't reach chemical equilibrium afterwards, will be diluted by this process. So, okay, first of all, the temperature evolution is important to avoid getting stuck here in the false vacuum forever. And as we mentioned before, if we want a new mechanism here, not just standard freeze out, we need the dark matter not to come back into equilibrium following the phase transition. And if this field, say, it depends on the model, but if this field here is oscillating a long time about this minimum before decaying, you'll also have a matter-dominated epoch following the phase transition. And in the end, the dark matter will be diluted basically by this additional expansion due to the inflationary epoch, and also by a possible matter-dominated epoch if the reheating temperature is sufficiently below the temperature at which inflation starts. This is simply the nucleation temperature, okay. Okay, so for this dark matter dilution, we require that the nucleation temperature is far below the critical temperature, which is somehow generically possible in close to conformal potentials. And some examples, one example would be the Coleman-Weinberg potential coming from radiative symmetry breaking. And actually, this was studied in the context of diluting dark matter in this paper called Supercooled Dark Matter by Thomas Ambai and Daniele and Strumia in 2018. Another So this is sort of the launching off point for our work. Another example that's known from literature are confining theories with a light dilaton, and which is going to be the focus later on in the talk. And then third of all, you could have somehow the holographic dual to that, which is like a Randall-Sundrum scenario with the Goldberger-Weiss mechanism to stabilize the extra dimension. Okay, so now we wanted to extend this dilution of dark matter from a phase transition from a short period of inflation to composite dark matter models. So what we're going to do is we're not going to specify the whole UV theory. I wouldn't even know how to begin to do that, but we're going to just assume that there's a strong sector confining at some scale F, and then along with the dark sector gluons, there are a number of massless quarks. So whenever I say gluon or quark, it's going to be the like techni quanta from this strong sector, not the standard model ones. The dark matter will be a hadron stable due to some underlying global symmetry of one of its constituent quarks, such as baryon number or strange like K mesons in the if there weren't any strangeness violating weak interactions. And the dark matter will be a composite state with mass of order F. And eventually the strong sector will communicate to the standard model via this dilaton portal. You can have different realizations, but that's what I'm going to be talking about later. So we can simply assume that there's some strong supercooling or motivated from theories with a light dilaton. And this light dilaton arises if the beta function of the strong sector is small when the theory confines. So this isn't somehow a generic thing. This doesn't happen in QCD, right? Where you just have a crossover, you don't have a strong phase transition. But there are ways of estimating the supercooling. And our approach was based on this paper here by Rotazzi and co-authors. And you can see here, basically, we've taken their way of approximating these sort of phase transitions. So they're assuming that all the other composite states are heavy compared to the dilaton, and then relating the dilaton mass to the beta function of the theory. So a lighter a lighter mass will imply a smaller beta function and a stronger phase transition. And then there are some details, right? So the strength of the phase transition depends on this parameter Z, which is basically a renormalization of the kinetic term of the dilaton. And then there are some details that depend on like the rank of the strong sector gauge group, because they're assuming that in the deconfined phase, there's some radiation present, which grows like this. They're assuming some strong sector effective degrees of freedom for the radiation. Okay, and so they match this. What's known for the radiation, the free energy, they match this onto the potential at slightly larger field values, where the VEV of the dilaton, which sets the strong scale, is larger than the temperature. So there's some way of estimating this, and this is a result of such a computation. And you can see when you go to light dilaton masses, you get some appreciable number of E-foldings for your inflationary epoch. So the difficulty we immediately ran into was that with this strong supercooling, the elementary technical quanta are going to be separated by large distances. So D is set by 1 over the temperature. So the distance is much larger than the size of the composite states when entering the bubbles. So the size of the confinement scale. Yeah? So we needed to estimate the dynamics of the string formation and breaking, which leads to difficulties. You don't have very good calculational control over this, but I'll present our modeling in the next slide. So in the end, also, not only do you form this string, which eventually breaks into a number of strong sector hadrons, but these hadrons also end up boosted in the plasma frame, which can lead to additional production via deep inelastic scattering as these hadrons return into kinetic equilibrium. So first of all, you take into account the dilution, but as I mentioned in the previous slide, basically you'll have this situation where these quanta are very far apart compared to the confinement scale when they first meet the bubble. So the picture is the following. Here we go into the bubble wall rest frame. So you can see the energy of this incoming quark is boosted by this Lorentz factor, which is just the Lorentz factor of the wall in the plasma frame. So this energy can be sufficiently high if it's larger than the confinement scale. For when this quark enters the confined phase, it will have enough energy to produce at least one hadron. Then we imagine that a string forms between the quark, which has entered the bubble, and the bubble wall. So the flux sort of confines towards the deconfined phase in a string. And then a number of the string, after a certain amount of time, basically given by 1 on F, it can break apart into a number of hadrons, forming your composite states. And your dark matter is going to be one of these composite states. Now, because you started off with one quark here, and then you have to form pairs of quarks from the vacuum along the string, you're left over with one quark, say, which doesn't have a partner. And so this guy has to be ejected back into the deconfined phase. And just on very naive dimensional grounds, we just took this energy to be of the order of F in the wall rest frame. And then the center of mass energy, okay, then you can derive this. Once you've done this, you can derive the center of mass energy of this system here. And then estimate also the inertia of the string, because this thing will be, the center of mass of this string will be moving compared to the wall, and so on. So in the end, with this naive modeling, we find that the yield, okay, you have this dilution factor, but then you also have this string, and it breaks into a number of hadrons. And then there's some, taking our inspiration from QCD and collider studies, there's some polynomial function of logarithms, where the argument is basically given by the center of mass energy divided by the strong sector scale. So in the end, we'll see that this model dependent, this function here, which I've suppressed, will not be important in the parameter regime we're interested in. So basically, the string center of mass the string center of mass Lorentz factor is different to the original Lorentz factor of the quark. So also these hadrons, which are produced, if you go into the string frame and the string fragments, the energy of the, back in the plasma frame, these guys are also boosted, yeah? Okay, so then, because they're boosted in the plasma frame, they can undergo some inelastic collisions in their return to kinetic equilibrium. And basically, under certain conditions relevant for us, the parameter space we're in, we estimate that the deep inelastic scattering with preheated particles produced by the oscillations of the inflaton, of the dilaton, will dominate in their return to equilibrium. So basically, in the end, what this does is that all the initial, if you agree with our arguments, all the initial strings energy in the plasma frame gets converted into strong sector hadrons, but only a small fraction of these, taken into account by this branching fraction or pseudo branching fraction, only a small number of these are that end up being the dark matter. So we imagine the other ones decay quickly into say the standard model or dark radiation or something else. Yeah. Okay, so we also remember there was also these ejected quarks, and we checked that they don't stop the incoming quarks from entering the bubbles. They don't change their energy by a large factor, and that these also confine in opposing bubbles, which more or less just doubles the yield. So taking this into account, here I've got a plot of the supercooling. So the nucleation temperature over F on the x-axis. So here's 10 to the minus 3, 10 to the minus 4, so on. And here I've got the yield. And if you just had an elementary relic, you'd have some yield like this green line here. Then you have this logarithmic enhancement, which increases the yield if you take into account the breaking of the string into that number of strong sector hadrons. And then eventually this deep inelastic scattering really boosts the yield up again. So you end up with many orders of magnitude more of dark matter than you would have otherwise, up to the, playing around with this branching fraction. So in some elementary dark matter models, this will just be 1. So you can compensate a bit. Okay, so you see this massive enhancement. And then finally here, note there's some change in behavior on the right here. And that just has to do with the behavior of the wall, that in this, when you don't have much supercooling, the wall no longer runs away, doesn't accelerate until collision. That's just that effect there. So this was just a very rough overview of what we looked at and how we tried to estimate this, because at the start we were really struggling to come up with some picture on how to estimate this. So if you have some other ideas, some improvements we could make, I'd be interested in hearing about it. Okay, but then taking this, just assuming that this is a realistic picture, then we can look at the the parameter space of this composite dark matter in the light of the supercooling, right? So here we have the dark matter mass on the x-axis, and again the supercooling on the y-axis, and we assume a cross section for the dark matter after it's in the confined phase of basically like 4 pi over m dark matter squared, something like this. Just that it's annihilating. So if you go to light enough dark matter, the cross section is large, and so everything comes into equilibrium following the phase transition, and you just have standard freeze out here. That's this line here. And then if you go to much heavier dark matter, then the cross section is getting smaller. And then you get these effects from the supercooling. So this would be the standard supercooling line, and then adding these additional effects, the string fragmentation and the deep inelastic scatterings. And if we go to heavy enough dark matter, then basically the Lorentz factor of the wall is insufficient for the incoming quark to produce one composite state, and they would all be reflected. And our paper was already long enough, so we just cut off this part of the plot. Okay, so this was, yeah. Okay. Okay, so that was the kind of generic picture, and then we wanted to link more to some phenomenology. So we looked at this dilaton portal because we already motivated our strong phase transition from these light models with light dilatons. So here, this would be then basically you have the dilaton here, the excitation of the dilaton sigma, talking, for example, in this case, to scalar dark matter. And then inspired by composite Higgs scenarios, we also take into account the couplings of the dilaton to the gauge bosons and so on. Yeah. So thanks to Jan for checking through all this. So then once you add these interactions, so this is motivated by composite Higgs scenarios. So the Higgs sector is sort of a PNGB of the strong sector. Yeah. Then we looked at these. Okay, then you can look at, now you have a way of calculating the cross section after confinement of the dark matter annihilation, indirect detection, direct detection, all sorts of things. And so this is what we find here. We have the dark matter mass here, and then basically the dark matter mass normalized to the strong sector scale, which basically is basically controls the coupling of the dark matter to the dilaton. And then for light dark matter masses, again, we have this standard freeze out scenario. So you can be sitting along this line, which is sort of an update to these earlier papers, which looked at the dilaton portal in like a WIMP-like context. Then you have here limits from xenon 1 ton and indirect detection and so on. So the heavy dark matter is still feasible here and can be tested in future experiments. And then eventually you hit the unitarity, the wall for unitarity here. And for much heavier dark matter, again, you can set the relic abundance. And here showing what nucleation temperature you need to set the relic abundance along these contours. And you can see here this dashed line. Up here, we have the situation where the reheating up here, the freeze out temperature is higher than the reheating temperature. So your dark matter doesn't come back into equilibrium. So then, because this is sort of interesting for the heavier, you can see on this plot, the heavier dark matter region, we can just fix the dark matter mass in terms of the strong sector scale. Okay, I just took an example here, 4 pi. And then this is just the same, this showed a very similar plot before, but now we have contours of the dilaton mass, which returns the required supercooling, and also, direct and indirect detection constraints. And here, we just show the region where this branching fraction we introduced earlier is between 10 to the minus 3 and 10 to the minus 6. So again, you have the standard freeze out here, and here you have the supercooling followed by all those novel effects. And the phase transition, so one obvious way of testing this region is gravitational waves, because you have a very strong phase transition. And here I provide some details. So the phase transition will complete through this bubble nucleation, and the bubbles will hit each other and percolate. And this will lead to a gravitational wave signal. Then you do the standard sort of abusive notation. The omega GW is the differential spectrum with respect to the logarithmic frequency interval. And then you have the spectra, which depend on the macroscopic properties of the transition, the latent heat, the inverse time scale of the transition, the Hubble scale when the transition occurs, and the wall velocity, which for us is the speed of light. So basically then, okay, there are a lot of uncertainties here because, the way you've estimated the dilaton potential and so on, and the dark matter yield. But just taking everything at face value just to see what comes out, okay, you can of course calculate these quantities, estimate them from the microphysical model, and then match onto results from simulations and semi-analytic studies. And the current what's coming out now in the literature is that for these very strong supercooled phase transitions, the gravitational wave spectrum seems to be captured by the bulk flow model. You can look in this paper by Thomas Constantine, which basically takes into account, compared to the envelope approximation, takes into account that there's some propagation of shells of the scalar field following the initial collision, and this can lead to some enhancement or changes to the gravitational wave spectrum. And this is backed up by simulations. So this is the plot taken by from a paper by Daniel Cutting et al. And you can also look at this paper by Marek Levicki and Ville Veskonen, which I believe find something similar. So you can see here, the colored lines are from the simulations. What's important for us is this orange line here, the dark orange line, the one at the lowest one here. And this comes from the model that Daniel Cutting and collaborators looked at, where you have the thickest bubble walls initially. And this corresponds to these cases with strong supercooling. And then the bulk flow model, which predicts this a drop in the frequency of basically the frequency to the -2, is roughly found also in the simulations here, -2.1. So that's the bulk flow model prediction here from the kind of analytic or semi-analytic study. And then below the peak frequencies sort of match. The amplitude is slightly reduced in the simulation by some order 1 factor. And then in the IR, it's not entirely clear, but it also, the spectrum seems to be going as frequency to the 1 power, like frequency 1 to the 1 or 0.9 here, rather than the old estimates, which were more like cube. Yeah. But eventually, we also know that one thing that isn't taken into account shown here is that eventually, okay, you have some very long wavelength or low frequency gravitational waves, which start off at super horizon scales, and it's known that these should scale as frequency cubed in the IR for initial super horizon modes, which enter the Hubble patch, the Hubble volume when in radiation domination. Okay. Okay, and then the simulations, you won't have missed this second peak here, but this occurs due to some very rapid oscillations following the phase transition. But this is somehow known to be unphysical just because of the lattice size that you can use in these simulations. So in a realistic cosmological phase transition, this would be all the way out in the far UV and suppressed, so you can't necessarily observe it. Okay, so then this is an example, okay, for these very strong phase transitions that we looked at, where the dilaton here decays rapidly into the standard model so that you get an unsuppressed signal. And you can see here the prediction from the bulk flow model of the phase transition. And you can see you're above the power law integrated sensitivity curves for these experiments, and also above the gravitational wave foregrounds, the stochastic gravitational wave foregrounds from galactic binary white dwarfs, extragalactic binary white dwarfs, and also the population of binary neutron stars and binary black holes inferred from the recent LIGO observations. And okay, basically, we also, in one difference here, what happens in the composite scenario, why you get such a large peak, is because of this rapid decay of the dilaton. So, and this arises basically because we're implicitly assuming the Higgs is a PNGB of the same sector that breaks the scale invariance. So you get this sort of coupling of the dilaton to the kinetic term of the Higgs. And in other realizations, you could imagine something more like in the Coleman-Weinberg case, where the reheating is suppressed. So you only have a very small portal coupling. And then you'd also have a smaller gravitational wave signal. So, okay, and the reason why I mentioned this is because for our scenario for the supercooling to work, you need to go to very large strong sector scales, which is perhaps not as attractive, doesn't solve the hierarchy problem anymore. So that's one of the downsides. So you need some other way of doing that if you want to. Yeah. So then just basically estimating the signal to noise ratios. I just, everything is above the foregrounds, but we just basically only take into account the signal above the foregrounds, a very kind of simple estimate. You can see the parameter region of this on this plot can be basically completely covered by a combination of LISA, which we all know about, and this beta SIGO, which is also a 3-satellite configuration, a proposed mission with a shorter arm length, which would be sensitive at higher frequencies. And eventually also Einstein telescope. So as you can see, because the signal is so, okay, we have this very, very strong phase transition. So the signal is large. Of course, we made a lot of assumptions to get to that. So in conclusion, the dark matter density could be set by a period of late time inflation terminated by a first order phase transition. And we saw a number of complications which arise in this composite dark matter scenario. But this dilaton portal, I think, offers at least an attractive scenario via testing via gravitational waves. So it's sort of motivating because there are scenarios out there that, if you have these strongly supercooled sectors, that can give you a big signal in LISA above foregrounds. And so I'm very much looking forward to the 30s. Yeah, thank you very much.
Iason, do we have any questions? I have a question. So how would you, what measurements can help you put this whole picture together? That this is that for example, the supercooled, the gravitational waves that you see at LISA are actually related to the dark matter, and this is the model of the world. What is the, is there a smoking gun? Is there a, what would be the path?
Yeah, I mean, I don't see an immediate way. If you see it's such a signal of, I mean, you'd know that there's a very strong phase transition in the early universe. So you know there's probably some there's some non-standard epoch of vacuum domination, say. Even, I mean, what's interesting is if you go back to the simulations, basically there is some difference in these curves depending on the type of transitions you have. Like here, I mean, if you go to the thinner bubble walls, so more like symmetric potentials, you already push up the frequency up a bit here, so you have a harder spectrum in the UV, but there's also large differences if you, okay, in these simulations, there's no plasma present, so there's no there's less there's a different slope if there's plasma present and so on. So you can disentangle get some information from that. In the IR, I have a plot. You can see very interesting effect in the IR. If after your phase transition, you go to a matter-dominated epoch, the super horizon modes then enter the Hubble scale during, some super horizon modes enter the Hubble scale during the matter domination. So you suppress the signal, but you also get this longer plateau in the IR. So you can pull out some additional information about the history of the universe, but it doesn't necessarily link you to the dark matter, unfortunately, as far as I can see.
So the dilaton is not discoverable, or there's no direct detection because you still have the, let's say, the dilaton portal.
Yeah, if the scale is low, then it's discoverable. If it's sufficiently low, but then you're back in the standard freeze out type scenario. Yeah.
Thank you.
If I can, there is a
Yeah.
so in the last final slide,
Filippo is gonna hate me because I forgot to mention this.
no. It's the
Yeah.
no, because he's a gravitational wave telescope guy. No, so actually telescopes. There is no telescope and exclusion or reach there. So you see a gamma and neutrino telescope with a question mark. The reason most telescopes stop at 100 TeV is that we never told them to look at, I mean, summarizing, some telescopes that have the potential don't look at those masses, but they could, they have the data. And some are starting to do it. For example, Antares or in the future Chem3Net. So at the moment there are no limits, but sensitivities are kind of promising. And so if you're lucky enough that, F is, say, dark matter mass is still below a PeV, so PeV is just our guesstimate, then one could hope to have a signal from gravitational wave and see even some sizable deviation or even some cosmic ray of that energy, and then one could hope to at least correlate a bit.
This is.
So here, dark matter annihilates primarily into dilatons, or even gauge boson. So this would shower and give you some signal, but anyway, you observe so few photons and stuff at that high energy that if you see something, I mean, you wouldn't have all the foreground mass that you have at lower energies. Yeah.
So yeah, I should say the way we estimated this is we took the plots from these future observatories, and we extended. The slope is pretty constant, so we extended that out and looked at where it crossed the unitarity constraint for the dark matter annihilation, and it interestingly goes up to about 1,000 TeV or so. So if you have super heavy dark matter with like cross-section around the unitarity limit, then you can go out there.
Can I ask a question?
Sorry, just wondering if you have this dark matter that is so heavy, and then you say it's further diluted, and shouldn't be the thermal cross section be smaller than usually expected in thermal production? So then you're below the kind of prediction for the generic 10 to the minus 26 or something.
Yeah. So I mean, yeah, you have a smaller, you have a maybe I didn't completely understand. I mean, the cross section is smaller than the usual thermal one.
Yeah,
But
right.
here I should say, okay, you also have this light dilaton. We take into account the Sommerfeld enhancement due to the light dilaton. And as you won't figured out, and it's important for the unitarity constraint as well. But yeah.
Right. Okay, no, I actually had another question. So in principle, you have this compression, localized compression. So maybe there, I mean, we have also effects of asymmetric particles there. So essentially that you have a region of space where you have particles that don't find a partner to annihilate with. So would you expect this also to happen in your scenario, at least in some parameter space, that you have essentially some sort of local asymmetry?
I don't know if I don't want to exclude it directly, but I don't know. I think I'll need to listen to your talk and then remember if it depends on the wall velocity at all. So you need some, I think maybe some slightly slower wall or something like this to have enough time for this compression. Is this? Yeah. Okay. I guess I'll hear soon.
Anyway, we can continue this afterwards because we can have discussion after the end of the talk. And I'm sorry to interrupt, but there is a talk from the online audience. So Michael,
Yes.
go ahead.
Yes, thanks. So you said something about when you were talking about the strength of the gravitational waves. You were saying something about the connection to the Higgs being a PNGB, and I didn't understand this. So can you maybe go back and explain?
Yeah. So basically, yeah. Okay. So when we have the phase transition occurring, and then we have this condensate, the dilaton condensate, and then when these walls are very energetic, and then they hit each other, and this will lead to this dilaton field oscillating about its minimum.
Sure.
And if this is slow, then you have this field oscillating about its minimum, and then you'll have a period of matter domination, which will suppress the gravitational wave signal because of the additional redshifting between the production and today.
But this is only if the dilaton is the lightest particle, no? If it can decay into lighter composite states, does that change it?
Yeah. So I mean, here we allow for the Higgs to be a PNGB of the same sector. So if there are other additional light particles, I mean, of the order of the dilaton mass, I think this EFT picture breaks down. So it's just, yeah.
I see. So sorry. So in the case there's the Higgs, the difference is that significant? So is that
the difference? I mean, you need some. Yeah. Okay. For the gravitational waves, you just need some rapid decay of the condensate. So you just need it could go into, I don't know, light dark sector particles or something like that. I mean, more generically. We looked at the gravitational wave signal. I've looked at the gravitational wave signal in the supercooled dark matter scenario together with Camilo Garcia-Salí, and they're basically there's a portal coupling between basically the exotic Higgs, which is gaining a VEV, and the standard model Higgs. And this coupling is very suppressed, and that leads to this long matter-dominated phase, because this exotic Higgs then takes a long time to decay into the standard model particles. But if you added something so that you have an additional decay channel, then you wouldn't have this suppression.
I see. Thank you.
Okay. Let's thank Iason again